At one end of a titanium plant is a pile of dark mineral concentrate. At the other is a silver ingot trusted inside jet engines, spacecraft, chemical plants, and artificial joints. The strange part is not that rock becomes metal. Humans have been doing that for thousands of years. The strange part is that almost every obvious way of making titanium can ruin it. Carbon can contaminate it. Air can harden and embrittle it. Even the furnace holding the metal can become part of the metal. So titanium cannot simply be smelted, poured, and shaped like iron. Before it becomes an ingot, the ore must be turned into a volatile liquid. Liquid must react with molten magnesium inside a sealed vessel. The product must then be broken out as a rough metallic sponge, and the sponge is only halfway finished. Why does one of Earth's most common elements require one of metallurgy's strangest manufacturing processes? To follow the answer, keep 4 transformations in mind. First, titanium-bearing ore becomes a chemical that can be purified. Second, that chemical becomes titanium sponge. The sponge becomes a uniform ingot. And fourth, some of the chemicals used in the process circle back to begin again. Ore becomes liquid. Liquid becomes sponge. Sponge becomes ingot. But each transformation introduces a new way for the titanium to fail. That is the real story. Titanium is not especially difficult to locate. It is difficult to separate without damaging the qualities that make it valuable. Titanium is among the most abundant elements in Earth's crust. But in nature, it is almost never found as pure metal. It is usually bonded tightly to oxygen inside minerals. That bond explains both titanium's usefulness and its manufacturing problem. At ordinary temperatures, titanium forms a thin oxide layer on its surface. That layer protects the metal underneath and gives finished titanium excellent resistance to corrosion. It is one reason titanium performs well in seawater, chemical equipment, medical implants, and other hostile environments. But when titanium becomes hot, the same chemistry turns against the manufacturer. Hot titanium can react with oxygen and nitrogen. It can also absorb hydrogen if moisture or hydrogen-bearing materials enter the process. Too much oxygen or nitrogen can reduce ductility. Hydrogen can contribute to embrittlement under certain conditions. The exact effects depend on temperature, concentration, alloy, and processing history. But the factory rule is simple. For hot titanium, the atmosphere is not empty space. It is a possible ingredient. That is why titanium production depends on sealed reactors, inert gases such as argon, vacuum chambers, moisture control, and equipment designed not to react with the material. The plant is not merely trying to extract titanium, it is trying to prevent the factory itself from becoming part of the titanium. The journey usually begins with 2 important minerals, ilmenite and rutile. Ilmenite contains iron, titanium, and oxygen. It is abundant and supplies a major share of the world's titanium mineral feed. Rutile is primarily titanium dioxide. It usually contains a higher concentration of titanium dioxide and less iron that must be removed before certain metal production steps. The difference is easy to remember. Rutile brings more titanium into the plant. Ilmenite brings more work. That does not make ilmenite a poor resource. Its abundance makes it extremely important. But before it can enter some production routes, much of its iron must be removed. Ilmenite may be upgraded into titanium-rich slag or synthetic rutile. The purpose is to increase the titanium dioxide concentration before the true extraction process begins. Many of these minerals are recovered from heavy mineral sand deposits. Mining operations excavate or dredge sand containing ilmenite, rutile, zircon, and other dense minerals. Gravity-based equipment separates heavier grains from ordinary sand. Magnetic and electrostatic systems then divide the remaining minerals according to how they respond to magnetic fields and electrical charges. This is not a miner discovering a shining vein of silver metal inside a rock. It is an industrial sorting process that separates millions of dark grains that may look almost identical to the human eye. After mining, washing, concentration, magnetic separation, electrostatic separation, and upgrading, the factory still has no titanium metal. It has only produced a cleaner titanium oxide. The titanium remains bonded to oxygen, and the obvious shortcut is exactly what titanium punishes. Iron ore can be reduced with carbon inside a blast furnace. Carbon removes oxygen, and the iron can be produced on an enormous scale. It seems reasonable to try something similar with titanium oxide, but at the high temperatures required, titanium can react with carbon and form unwanted compounds. The method that removes oxygen can contaminate the material in a different way. The obvious route fails, so the industry takes a detour that barely resembles traditional metal making. Instead of extracting titanium directly from the oxide, The plant converts the titanium into titanium tetrachloride, or TiCl. Titanium-rich feedstock is combined with carbon, commonly supplied in a form such as petroleum coke. Chlorine gas passes through the hot material at temperatures around 1000 degrees Celsius. The carbon helps remove oxygen, the chlorine combines with titanium. The result leaves the reactor as titanium tetrachloride vapor. Vapor can be cooled and condensed into a liquid. The factory started with dark mineral grains. Its next major product is not silver metal. It is a titanium-bearing liquid, and that strange change of form is the first major breakthrough. Solid ore contains titanium mixed with iron, silicon, vanadium, aluminum, and other elements. Separating those impurities directly from the solid material is difficult. Titanium tetrachloride can be handled differently. It can be boiled. It can be condensed. It can be purified according to the different temperatures at which chemical compounds vaporize and return to liquid form. Some impurities remain behind as solids in the chlorination reactor. Others form chlorides of their own and travel with the titanium tetrachloride. Those unwanted chlorides must be removed through settling, chemical treatment, condensation, and fractional distillation. The plant is not yet making titanium metal. It is making titanium separable. Distinction matters because a contaminant allowed through this stage may survive into the sponge, then into the ingot, and eventually into a component placed under enormous stress. The reliability of a finished jet engine part may depend on the cleanliness of a liquid produced much earlier in the process. Chemists understood that titanium existed long before they could make it commercially. In 1791, William Gregor identified evidence of an unknown element in dark mineral sand from Cornwall. More than a century later, Matthew Hunter produced relatively pure titanium by reducing titanium tetrachloride with sodium inside a sealed vessel. The method worked, but it was difficult and expensive to scale. During the 1930s, Wilhelm Kroll developed a route that used magnesium instead of sodium. Change created the foundation of the process that entered commercial production in the late 1940s. It took more than 150 years to move from identifying titanium in sand to manufacturing it at industrial scale. The delay was not caused by a failure to find titanium. It was caused by the difficulty of keeping it usable once it had been separated. Inside the Kroll process is a sealed steel vessel called a retort. Air is removed or displaced with an inert gas such as argon. Magnesium is placed inside and heated until it becomes molten. Purified titanium tetrachloride is then introduced gradually, not all at once. The reaction produces heat, and the feed must be carefully controlled. Depending on the reactor and plant design, the reduction may continue for days. The chemistry looks simple on paper. Titanium tetrachloride reacts with magnesium. The magnesium takes the chlorine. Titanium metal and magnesium chloride remain, but the physical result is nothing like a smooth pool of molten titanium. The reaction temperature is far below titanium's melting point, so the new titanium stays solid as it forms. It grows into an irregular porous mass inside the vessel. Magnesium chloride fills the spaces around it. Excess magnesium may become trapped inside. Different parts of the growing mass may experience different temperatures and different contact with the reacting materials. The reactor gradually fills with something that looks less like an ingot and more like metallic coral. When the reaction ends, the vessel must cool before it can be opened. That cooling time matters. The Kroll process is a batch process. The reactor is prepared, charged, heated, operated, cooled, opened, cleaned, and prepared again. Metal does not flow continuously from the other end. Each batch must complete the entire cycle. When workers finally open the vessel, they do not remove a polished bar. They find a rough titanium mass attached inside. It may need to be cut, pressed, chipped, or forced out with heavy equipment. Material close to the reactor wall may contain iron, nickel, or other contamination from the vessel, and may need to be separated from higher quality sections. This porous intermediate is titanium sponge. The name sounds soft. The material is not. For the first time, the process has produced titanium metal. But this is not the payoff most people expect. Titanium has been extracted. It has not yet been trusted. If you enjoy seeing the hidden process inside familiar materials, subscribe. Because producing titanium sponge solves only the first half of the problem. The sponge still contains residual magnesium and magnesium chloride. And the magnesium chloride created during the Kroll reaction is not always treated as simple waste. In an integrated production system, it can become part of another cycle. Magnesium chloride can be collected, purified, and sent to an electrolytic cell. Electricity separates the compound into magnesium and chlorine. The recovered magnesium can return to the reduction stage, The recovered chlorine can return to the chlorination stage. Titanium moves forward through the plant. Magnesium and chlorine circle back. The exact recovery system varies between facilities, and recycling requires energy and equipment of its own. But without it, valuable reactants would leave the process after every batch. The byproduct of one reaction helps supply the next. Titanium production is not simply a line from ore to metal. It is a chemical loop wrapped around a difficult extraction. Meanwhile, the sponge must be purified. Residual magnesium and magnesium chloride occupy pores throughout the titanium mass. One common method of removing them is vacuum distillation. The sponge is heated under reduced pressure. Magnesium and magnesium chloride leave the porous material and move toward a cooler part of the system where they condense. The titanium remains behind. Chemistry has now freed the titanium and removed much of what surrounded it. But that creates a second problem. The metal is still porous. It may still vary from one region to another. It may contain contaminated pieces near the edges. It may not contain alloying elements in the correct proportions. Extraction is complete. Proof is not. This is where the story changes from chemistry to engineering. The sponge is crushed into smaller pieces, then screened, sampled, inspected, and classified. Material with unsuitable chemistry or visible contamination can be removed from high-performance production. Acceptable sponge from different parts of a batch, or from several batches, can be blended to create a more consistent feed. That blending matters because a large sponge mass is not automatically identical from its center to its surface. The final ingot must behave as one material. The sponge did not form that way. Alloying elements may also be added during this stage. Commercially pure titanium is valuable where corrosion resistance, formability, or compatibility with the human body matters. Other applications require stronger titanium alloys. One of the best-known combines titanium with approximately 6% aluminum and 4% vanadium. But the recipe alone does not create a reliable alloy. The ingredients must be distributed uniformly. A component cannot contain one region with the intended composition and another region that responds differently under heat or stress. So the sponge must be melted. And melting titanium creates a new version of the original problem. Titanium melts at roughly 1,668 degrees Celsius version of the original problem. Titanium melts at roughly 1,668 degrees Celsius. At that temperature, ordinary air can contaminate it quickly. Many conventional furnace linings and ceramic crucibles can also react with the molten metal. Titanium cannot simply be dropped into an ordinary furnace and poured into a common mold. One widely used method is vacuum arc remelting. Titanium sponge, suitable recycled titanium scrap, and measured alloying additions are pressed into compact shapes. Those pieces are assembled into a long, consumable electrode. The electrode is placed inside a sealed chamber above a water-cooled copper crucible. The chamber operates under vacuum or a carefully controlled inert atmosphere. An electric arc forms between the electrode and the metal below it. The end of the electrode melts. Drops of titanium fall into a molten pool inside the crucible. As the electrode is gradually consumed, the pool grows and solidifies from the bottom upward. The ingot builds itself one controlled molten layer at a time. The copper crucible is water-cooled, so the titanium freezes against it rather than reacting extensively with the container. Even here, the factory is still solving the same hidden problem. The equipment must touch the titanium without becoming part of it. For demanding grades, one melting cycle may not be enough. The first ingot can be removed, inspected, conditioned, and used as the electrode for another vacuum arc remelting cycle. Some critical materials may undergo multiple melts to improve chemical uniformity and reduce the risk of harmful inclusions. That repetition is expensive. It is also why the metal can be trusted. An aircraft component cannot be reliable only in most places. A medical implant cannot be clean on average. A single hidden region with the wrong chemistry can matter more than the thousands of kilograms of metal around it. The expensive part is not obtaining titanium atoms. Those atoms were present in the original mineral. The expensive part is creating a large mass in which those atoms are arranged, alloyed, and purified consistently enough for an engineer to place the material under extreme stress. Other melting technologies can also be used. Electron beam furnaces use high-energy electrons to melt titanium feedstock under vacuum. Plasma-based systems provide another controlled source of heat. These methods can consolidate sponge and scrap and may help remove certain volatile impurities, but every melting route is answering the same question. How do you melt titanium without allowing the atmosphere, furnace, electrode, or container to undo everything the earlier stages achieved? Once the ingot is accepted, the process begins to look more familiar. The metal can be forged into billet or large shapes. It can be rolled into plate or sheet, drawn into wire, extruded into sections, or processed into bar and tube. Heat treatment can control the internal structure and final properties. Then the metal must be machined into actual components, and titanium remains difficult even here. Titanium does not carry heat away from the cutting zone as efficiently as some common metals. Heat can concentrate near the cutting tool. Tool wear can rise. Cutting speeds may need to be controlled carefully. Large aerospace parts may begin as heavy forged pieces from which a substantial amount of material is removed before the final shape appears. The finished component may look light and elegant. Its manufacturing history is neither. First, the mineral is concentrated and upgraded. Then it is chlorinated and distilled. Magnesium frees the titanium, and vacuum removes what remains. The sponge is crushed, inspected, blended, pressed, melted, and sometimes remelted. Then the ingot is forged, machined, and inspected again. Titanium is not expensive because any one of those steps is impossible. It is expensive because nearly every step must protect the metal from the next source of contamination. It is also why the Kroll process has been so difficult to replace. Researchers have spent decades exploring methods that might produce titanium directly from oxide, operate continuously, use less energy, or create powder closer to the final component shape. Some alternative routes have produced promising results, but a replacement must do more than create gray metal. It must produce large quantities with low oxygen, controlled nitrogen and hydrogen, predictable alloy chemistry, limited contamination, competitive cost, and repeatable performance. A new process does not succeed because it produces titanium. It succeeds when engineers trust that titanium enough to put it inside a jet engine. That is a much higher standard. There is one final irony in the entire industry. Most titanium minerals have historically not been used to make titanium metal at all. They have been used to make titanium dioxide pigment. Titanium dioxide scatters light extremely well, which makes it valuable as a bright white pigment in paints, plastics, paper coatings, and other products. A white wall and an aircraft component may begin with titanium-bearing minerals from the same broad supply chain. One industrial route preserves titanium's bond with oxygen because the oxide is the desired product. The other spends enormous effort trying to break that bond. The titanium in paint is not unfinished metal. It is a successful oxide. Metal production is the difficult exception. That changes the way the entire process looks. The factory is not opening a mineral and discovering a finished metal trapped inside. It is guiding titanium through a series of chemical and physical airlocks. The mineral is concentrated. Iron and other unwanted material are reduced. Oxygen is replaced by chlorine. Unwanted chlorides are distilled away. Magnesium removes the chlorine. Vacuum removes magnesium and salt. Melting removes pores and reduces chemical variation. Inspection searches for what the earlier stages may have missed. Each door closes before the next can open. And behind every door is another substance titanium might absorb. Now return to the two objects at the beginning. The dark mineral concentrate. The silver ingot. The mineral never lacked titanium. What it lacked was separation, consistency, and proof. Rutile begins closer to the target. Ilmenite requires more upgrading before the real extraction can begin. The oxide becomes a purifiable liquid. The liquid becomes titanium sponge. The sponge becomes a uniform ingot. And magnesium and chlorine circle back, so another batch can begin. By the time the ingot appears, titanium's story is no longer about what the factory added. It is about what the factory kept away. Oxygen, nitrogen, hydrogen, magnesium chloride, reactor metal, hidden inclusions. The ingot is valuable because all of those things failed to become part of it. That is controlled absence, and it is the real product of the titanium factory. Titanium does not emerge from the ground looking futuristic. It earns that appearance through one of the most elaborate journeys in modern metallurgy. Not a rare metal hidden in a rare stone, a common element that refuses to come out alone. Which transformation surprised you most? And to see another ordinary material hiding an extraordinary process, watch the next video on screen.